We have already talked about reactions in the context of organic chemistry a little bit, but all the reactions we've talked about so far have been acid-base reactions. And so we're starting to move into real reaction chemistry of a different variety involving, say, carbons as opposed to just acids and bases. And the first one that we're going to start with is one that we call an SN2 reaction. And the SN2 stands for Substitution Nucleophilic Second Order. So what's going on? Well, imagine you have methyl chloride and some I- floating around. Then it's possible that this will go ahead and cause a reaction with the methyl chloride that leads to methyl iodide forming and Cl- floating around. This is a substitution reaction because the identity of the group bound to the carbon changes. And it's a nucleophilic reaction because I- serves as a nucleophile. This comes in and donates a pair of electrons to the carbon, which pushes the chloride out. So this is the nucleophilic part of it. And the second order part of it has to do with kinetics. So if you have taken Chem 190 or Chem 120, then you may already be familiar with the concept of kinetics describing a chemical reaction. And in the case where two things must collide in order to have a chemical reaction take place, we call that second order. So what this is really talking about, the second order part, is a rate expression. So the rate of this reaction is going to be determined by some rate constant times the concentration of the starting substrate, methyl chloride, and the concentration of the attacking nucleophile. It's a second order reaction because in the elementary steps, the two molecules must actually collide. So the methyl chloride and the iodide must collide in order for a new reaction to take place. The more methyl chloride you have, the higher the concentration of this, the faster the reaction goes. The more iodide you have, the faster the reaction goes. Again, since the rate depends on the quantities of both involved, because again, they must collide, then this is a second order reaction. This is fundamentally defined in terms of kinetics because that's how we figured out the mechanism in the first place. But the fact of this collision really determines how the reaction goes. So we need to talk about some of the other factors. Okay, so I've decided to generalize the reaction a little bit. Rather than having, say, methyl chloride, what we have is some carbon-containing substrate. R is something that I don't want to define, so this could be basically anything, as long as it's got two hydrogens there, say. And then we have a leaving group bound to. In terms of what the chloride is doing, it's leaving. We call that a leaving group. So we have a carbon and we have a leaving group bound. We also have some nucleophile floating around out here. And the substitution reaction involves the nucleophile attacking this carbon right there and causing the leaving group to leave. So the nucleophile comes in and attacks this carbon, which causes the leaving group to leave. Again, the kinetics for this process, which is why it's a second order reaction, depend both on the concentration of the substrate, which is to say the carbon with the R in the leaving group, and the nucleophile, the thing that's doing the attacking. Both must be present. Okay, so if this mechanism is taking place the way I've described, then it happens all in a single step. The nucleophile comes and starts to make a bond to that carbon, and the leaving group leaves. The nucleophile has extra electron density. In fact, frequently, like in the case of I-, it is deemed to be an actual minus charged thing. And so we tend to describe this in these terms as nucleophile, or perhaps even nucleophile minus. It is almost always going to be at least nucleophile delta minus. But this is going to be a highest occupied molecular orbital, or nucleophile, that's doing the attack. And where it's attacking is going to be the electrophile. So we call the substrate in this case the electrophile. And in particular, it is the backside of the carbon leaving group bond that gets attacked because that's the lowest unoccupied molecular orbital in the entire system. Which orbital in particular is getting attacked? Well, the carbon leaving group bond, whatever that is a sigma bond. And so what's actually getting attacked is the sigma star bond that sits right here. So the lowest unoccupied molecular orbital is the sigma star bond between the carbon and the leaving group. And that's the position that's electrophilic. So what we have is the nucleophile sitting right here, and it comes and it starts to push electron density into this carbon leaving group sigma star orbital, which causes the original orbital, the sigma bond between the carbon and the leaving group. This bonding orbital starts to lengthen, and eventually it dissolves completely. Said another way, what we have is at some point a carbon that is at least partially bound on both sides to the leaving group and partially bound on the other side to the incoming nucleophile. The incoming nucleophile is pushing electron density into this orbital and starting to create a bond, but the fact of pushing electron density into the sigma star orbital has the effect of lengthening this one. And eventually, all that electron density is pushed in, and all of that is broken, and what you're left with then is your product. So the nucleophile has to approach from the backside of the carbon leaving group bond, because that's where the main lobe of the sigma star orbital. And you're going to fill that sigma star with electron density, and that's going to cause the leaving group to leave from the other side. The nucleophile is coming in from the back, the leaving group is leaving out the front, and the result of this is now the nucleophile is bound to the other side. This particular system is achiral because there are two hydrogens bound there, but if it were possible to tell what the stereochemistry was, then the result of this, it would be an inversion of the stereogenic center. Again, this is not a stereogenic center because there are two hydrogens, but the nucleophile must come from the backside in order for this reaction to take place. I also hope to convince you that there's a good reason why it's attracted to the backside of the molecule, and that is, if you think about what many leaving groups are going to be, and we'll talk about this more later, the leaving group is almost always going to be some electron-rich thing, something that has electron density on it. Said another way, the end of the molecule that has the leaving group on it is always going to be delta minus, which means that the carbon that the leaving group is bound to is always going to be delta plus. So if you're a nucleophile that's floating around out here in outer space, and you see this molecule, you're going to be attracted to the backside, the delta plus, as opposed to the leaving group side. You're going to be repelled by the leaving group side because that's where the extra electron density is, and you're going to be attracted to the backside because that's where the lack of electron density is. So pure electronics governs the interactions between these two molecules. Once you start donating electron density into that antibonding orbital, then you go through some transition state and you end up inverting in the product. I mentioned the term transition state because I want to directly have you thinking about reaction coordinate diagrams here. And so what I'm drawing is, you're starting at some starting material, which is to say the substrate, the R plus the leaving group, with some nucleophile floating around, and they're at some energy. And then you go to products, and presumably they're at a lower energy, where the R is now bound to the nucleophile, and the leaving group is free to float around. In order to go from one to the other, you have to go through some higher energy transition states, some place where things are partially built and partially broken, somewhere where the nucleophile is partially bound and the leaving group is partially dissociated. That's why this is at higher energy. But in any event, you have to pass through some higher energy state on the way there. However, this all happens in a single step. There is no low energy intermediate that you stop at. Instead, you simply go over the hump and then down the hill onto products. So the reaction coordinate diagram for an SN2-like process is going to be one that goes from starting materials directly to products. You pass through a single transition state. There are no intermediates along the way. So let's draw out another example of an SN2 type reaction. Here I have a bromobutane molecule that actually happens to be chiral in this case, and it is the R enantiomer. So we have an R bromobutane, and then floating around nearby we have some of this sodium thiol species. And so let me go ahead and redraw that the way an organic chemist thinks about it. And it is to first identify that the sodium is almost never important. So really, that's sodium plus floating around. And then what do we have floating around nearby? Well, some thiol species, and if the sodium is plus, then this has to have a minus on it. So this is really the system that we're dealing with. We have a sulfur with a minus, we have this system here. So now, what is this substrate? Well, we have a leaving group. Halogens are the typical leaving groups. So we have a leaving group and a carbon chain. So what happens? Well, mechanistically, you're going to have a flow of electron density from the thing that has too much electron density, the sulfur with a minus on it, to the backside of the carbon-bromine bond, partially because that's where the delta plus is, mainly because that's where the LUMO is, the sigma star of the carbon-bromine bond. But as you push electron density into that orbital, you cause the bromine to leave. This happens all simultaneously in one step, and the result is that you make a new product with inversion of stereochemistry. So now the sulfur, because it must have attacked from behind, will end up bound in the other configuration. So this is going to be the S enantiomer. Again, priority 1, 2, 3. This was the R enantiomer, priority 1, 2, 3. So this needs to be the S because the hydrogen is pointing toward us. So again, we get inversion of stereochemistry because this is an SN2-like process. Meanwhile, floating around, left over from this is the Br-, and of course we have the leftover sodium, and so those are now possibly going to interact with each other or not. I couldn't really care less. Traditionally, these reactions are run in some solvent, and that solvent tends to be something like, say, acetone or DMSO, so arguably I will just choose acetone, and this was the reaction. Classic SN2 type reaction. A decent nucleophile, a good leaving group, some reaction takes place between the two of them that inverts stereochemistry if it's possible to see that, and that's a substitution reaction in a nutshell. So this is classic SN2 reaction. It won't surprise you to learn that I have a nerdy SN2 chemistry t-shirt, and one of the key points that you'll see in any of these sort of t-shirts is always that the nucleophile is attacking the backside of the substrate. In fact, the way that SN2 reactions are almost always described is as taking place via stereospecific backside attack. What does this mean? It means that the nucleophile will always attack the sigma star orbital opposite the leaving group, partially because the leaving group is delta minus and the nucleophile is delta minus, meaning that this is the delta plus spot, so that the nucleophile will come and fill the sigma star orbital. This then proceeds through a transition state that will always be a pentavalent species. The carbon will actually briefly have 5 things trying to make bonds to it. It will end up transitioning from one particular stereogenic center to the other. It will invert. And again, this must happen because of the electronics. The nucleophile must attack from the back. The leaving group then gets kicked out and the stereochemistry inverts. So SN2 reaction, if you're going to remember a single phrase, it is stereospecific backside attack. You're going to attack from the back, you're going to go through some transition state, you're going to end up inverting the stereochemistry in the product. Alright, let's change the system ever so slightly. We're still going to keep the same reactive substrate there, but now what I'm going to do is I'm going to change the other reactant. And I'm going to say that rather than running this reaction in acetone, maybe we run this reaction in, say, DMSO, again, another solvent, and now we're going to go ahead and add in, say, methanol. And I don't know if this reaction will go at room temperature, so maybe we heat this reaction. So what are the products in this case? So what do we have? We have an area of a lack of electron density. We have something with a decent leaving group. DMSO is a solvent that you will encounter all the time, and it stands for dimethyl sulfoxide, which is to say that it's just a solvent. It's not going to interact in the reaction, but it's really polar, which tends to speed up SN2 reaction. I'm adding heat to this reaction. I'm trying to drive this on, even if I have a relatively bad nucleophile. This oxygen over here is a relatively bad nucleophile, but it does have electron density. So maybe I could imagine pushing electrons onto the bromine through some process that first attacks the carbon and then the carbon-bromine bond goes like that. Again, SN2 reaction. Again, I'm going to do an inversion of stereogenic center, and now I have the oxygen bound as well as there's still a hydrogen bound at this stage. Why is there a hydrogen bound? Well, because this was methanol that was doing the attack, so that hydrogen hasn't gone anywhere, it's still attached. What do I have floating around in solution at this point? Well, I have Br-, and it's eminently possible that the Br- will come along and remove, say, that's hydrogen, leaving then the final product. However, HBr is one of the very strongest acids known to man, so it's highly unlikely that that is the thing that's going to do it. I illustrated it because we just generated Br-, and so you might think, oh, the minus is going to be attracted and pull off that hydrogen. In practice, though, it's far more likely that the base that's around and capable of doing this is another unreacted molecule of methanol. That is almost certainly the actual compound that will come by and remove that proton. Most of the time in organic chemistry, though, we don't necessarily care about the identity. So what often we will use is some base that comes in and does this deprotonation. What is the product that we end up making when all is said and done? This methyl ether. Left over, in some sense, is an H and a Br, and they may or may not end up bound to each other. It kind of doesn't matter. The thing I always care about is the main organic substrate, and in this case, it's going to be that. So the core of the SN2 reaction is as drawn. we have some nucleophile present. If there is no nucleophile present, no substitution can take place. We need to have a substrate, and a leaving group needs to be bound to the substrate. Again, if we don't have a leaving group at all, no reaction can take place. You mix these two together, they may be some solvent present. If not, one of these two molecules in principle could be the solvent. And if you mix these two together, what happens is a single displacement reaction. There's a single collision that takes place between the substrate and the nucleophile. The rate of the reaction depends on both the concentration of the substrate and the concentration of the nucleophile. They all happen all at the same time. You go through a single transition state, and you end up with the nucleophile bound to the substrate. And the stereochemistry, if it's possible to tell, is going to be inverted, because the nucleophile has to come from the opposite side of the leaving group. So your product is the nucleophile bound to the substrate. Possibly there's some acid-base chemistry that happens after that. And then you have the leaving group left over. In a nutshell, this is the core of the SN2 reaction in its most general form. You need a nucleophile, you need something to react with. That something needs to have a leaving group that's good enough to leave. You probably have some solvent, although it may be one of these two reactant partners. The product will end up inverted, stereochemically speaking, and the leaving group is then gone. So what determines the success or failure of the reaction? What determines how fast the reaction is going? The identity of the nucleophile clearly matters. The more nucleophilic the nucleophile, the better this reaction goes. The better your leaving group, the better this reaction goes. The size of the substrate has to matter. All of the attacks are happening from the backside. So size, degree of substitution of the substrate has to be important. Solvent for an SN2 reaction also clearly matters. These are many of the factors that go into whether a substitution reaction can take place or not.